Hello, Mr. Harry, are you alright? Yeah? Okay, so yesterday we talked about the chromosome, the A, what's that? Human gene, yeah?
Yes.
Yeah? So given a gene group, we want to find the number of mutation group for the gene, yeah? So A pairs with what?
T.
And C pairs with
G.
Yeah. And how are we using it? We're using the depth first search, right? Remember, depth first search. Do you still remember? That's from yesterday. Yeah? We go, this is the genes. Answer equals 0. So that genes is the vertex, yeah? Each vertex. And we want to start a breadth search as long as it's not visited, right? It's not visited. Then we start a depth search with the vertex. We increment the answer, right? Alright?
Yes.
Can you stop that, please? ACCT, the neighbor, its mutation only by one difference is GCCT. Right? So there's an edge between these two vertices.
First letter.
Yeah. So there's an edge between these two vertices. So then when I do this depth search, I find out, I brute force the possibility of one letter difference, and then I check if there's a vertex for it, then I depth search. So in other words, when we do this depth search, we try to visit all the vertex connected to current vertex, right? And then when we visited these components, and then we try this one, yeah? At the same time, we mark it as 1, and then we do the depth search. So what's here? So this is the depth search for the graph, right? But for this one, we can do this depth search as well, right? So for here, I can do this, right? If there are other vertex here, yeah? Yeah? We can do this depth search to connect all the pieces, to mark all the pieces. We can also do the breadth search, right? Yeah? It will be the same, right? Make sense? Okay.
Yeah.
Okay. So do you still remember how we implement the breadth search?
Genes.
Yeah. How do we implement the breadth search?
You did it in depth search.
This is depth search. Now I can change this to breadth search and change this to breadth search. Yeah? But obviously I still need to do a little bit more work, right? So how can we do this? For the breadth search.
Q.
Yeah, Q, yeah, exactly. Okay, so this breadth search, I just need to erase all of it. But this thing is the same, right? So we haven't finished this yet. So this still works, okay? So for answer equals 0, this stores the number of connected components, right? We want to find out the number of, the number of what? Islands or whatever, yeah? The trees, yeah? The number, or could be a tree, could not be, yeah? Yeah? Maybe not a tree, okay? Isolated, what do you call it? Isolated component, okay? Components. So the task is to find how many components are there, right? So we start with any vertex in the component, we do this breadth search or depth search. Yesterday we talked about depth search, now we're focusing on the breadth search. So in order to implement breadth search, what kind of data structure can we use to implement the depth search?
Recursion.
Depth search is recursion, and how about breadth search?
Breadth search is Q and depth search is stack.
Yeah. Okay. So Q, yeah. First in, first out, yeah. First of all put a node, yeah. Put a node A here. We take it out. We put its connected neighbor, yeah. Could be 4, right? Yeah. And then we take one out. We push the kids on the right hand side. Append, right? Top left. DQ, double NDQ, yeah. Yeah. Okay. Okay, so let's do this. First of all, we convert these genes. This is the list of vertex. Yeah, list of vertex. We convert it to a set. So let's say G equals set gene. Why are we converting this to set? What's the advantage if we convert the list into set?
It will be O1.
O1 lookup. Yeah. Oh yeah. Yeah, so if we want to find out a number like this, yeah, 1, 2, 3, or whatever. If we want to find, for example, 3 is in the list, yeah, this is the list. That's on, right? On time to look up in the worst case, because the last one, it finds it sequentially, right? It checks if the first element is the one you're looking for. If yes, that's great, right? If not, keep going, keep going. So in the worst case, it needs n iterations before it finds it or not, right? But if we converting this to a set, then we can just say an element in set A, right? In set A, then that's a 1 because of the hash key, hash table. Yeah, we talk about the hashing. Yeah. So we convert it to a set, and then we can do this. Define for search A. First of all, I put a q equals dq, and I put a root which is A in it, right? Put it at the beginning. So this is the node A, right? And then here B, here will be C, I don't know, D, and then here will be another node. Yeah? This is a graph, right? Graph. Yeah? Undirectional graph. If it's not connected, yeah, it's not connected. Alright?
Yeah.
So, okay. So put an A and then wire there's an element in the queue. We take the queue out, current equals q dot
Pop left.
yeah, pop left. And then we need to look at we have this AC, this A, okay, current equal could be a string, yeah, AC, CT, whatever, okay. So what's its neighbor? How do we generate the neighbor? We can try to replace each letter with 4 possibility, right? That could be its neighbor, right?
Mm-hmm.
Yeah. So we need to try every possibility for the each letter. We try its neighbor. How many neighbors does it have?
3.
Yeah, that's a good one. It's 3. It's not actually, yeah, because the numbers of genes are unique, right? So we don't consider the duplicate, right? So we don't need to consider itself, right? So it's 3 because if a letter C, then there will be other 3 choices. But we can, you know, we can simplify the implementation, right? I show you. For I will be the index. In range, length current. Okay, and then now I want to try to substitute this index I with other choice, yeah? So for x in, you said there are 3 choices, but let's list all the 4 choices. A, C, G, T, right? Yeah, because look at this pair, right? A covers T, C will be G, right? But we are considering just this is the genes, number of genes, yeah? For the inside a chromosome, a human chromosome, yeah? Human has 23 chromosomes. One of them is the gender, right? XX is the girls, XY is the boys.
Mm-hmm.
And each chromosome has hundreds of these pairs, right? And A matches T, and C matches G. So it's very robust, right? So one of them is broken, the human can repair it, right? Yeah. So that's called DNA. Yeah.
How can you repair it?
Look, this is broken, and you just look it up. This is A, so this must be
T.
exactly. Yeah. You see, unless these 2 are broken. So the chances of 2 broken at the same time is less likely than 1 broken, right? Alright? Make sense?
Mm-hmm.
Yeah? So it's like 2 servers. 1 server go down, could happen, right? But 2 servers at the same time going down is a lot less likely, yeah?
At the same time.
At the same time, yeah? The chances are less likely, right? Because for example, like maybe this 1% of time goes down, right? And this is another 1% goes down. So what's the probability of these 2 go down at the same time? You do what? What operation for this? This is 0.01, and then this is 0.01. So what's the probability of both going down?
0.00.
Yeah, you multiply them together, right? Yeah? So what's the chance? 0.000001, right? So what's this chance? It's 0.01%. Okay? You see? And if there are 3 servers going down,
But first you did 3 zeros after the decimal, but then you took 1.
sorry, what do you mean?
You did 3 zeros here, but now you did 1.
0.01%. This is percent, so you need to divide by 100 here. So put another 2 0. Yeah, so that's 3 0. That's fine. Yeah, okay. So another computer going down at the same time, you multiply, right? Yeah, make sense? Yeah, we talked about the probability before, right? So one of them they are okay. So there are two coins, yeah, 2 coins.
What?
So a box, this box can have a coin or have 50-50, and then here is 50-50. Okay, so both boxes not having a coin. What's the probability? 50% has coin, 50% has coin. And what's the probability of both not having any coins in there?
There is
You do what?
times
Times those, so that's, what's this?
a quarter.
A quarter, 25%, yeah? Exactly. And another one,
0.25.
yeah, another one, you just keep dividing, yeah? Keep times half, right? Okay?
Half and then half.
Yeah, you see?
Until you get 1 baby.
Yeah, right. Okay, for x in this, then the n, the new one would be current, current up to I. So look here, this is I, yeah? Current up to I. I want this part. Look at it. This is I want this part. Plus x, this is the 4 possibility, and plus this bit here. So which is current I plus 1 to the n, right? Yeah, this is neighbor. I try each possibility, and then I just have to check if n in G, right? We have this one, right? If we have this one, then what should we do? First of all, what should we do with this? If we have found a neighbor, what should we do? What should we do?
If we find a neighbor, we shall
What?
move.
Remove, yeah? Remove, yeah? G dot remove, right? Remove n, and what should we do next?
Append
N, append to what?
Q.
Q dot append n. We're done. Yeah? And that will be, that's the breadth search. Okay? So, what's the difference? Is this one. Yeah? We're going through each vertex. If it's not being marked visited, instead of doing depth search, we're doing the breadth search. Because the target, our target is the same. Our target is to follow the edges, to visit all its neighbors. Yeah, could be many neighbors. Yeah, could be connected. Look, Eric, it could be many. Right, Eric. Look, which way here? So with the depth search, you just visit all of it. Yeah. With the breadth search, you still visit all of it. Mark it as, visited. So how do we mark it visited? We remove it from the G. This is G will be a set of the vertex which has not been visited. So once we visit it, we remove it from the G, right? So we just remove it. Yeah, remove it. Yeah. And once we mark it, then we continue to visit those vertex which has not been visited, right? But once when we start it, we need to increment the answer equals 1 because that we start another new component, right? So this target is to find how many different components. Okay, that's it for today. Bye bye. Bye bye.